Welcome everyone to the next lesson in this series, and in this video we will look at overlay networks with Calico. Now, one of the primary functions of the CNI is to provide pod-to-pod connectivity, and we looked at this in the previous lessons. Now, this tends to be relatively easy when the nodes in the cluster are in the same network, as in the same network subnet. However, it's possible that the nodes in your cluster are in different network subnets, or as your cluster grows, it's possible that you may add nodes that are in different network subnets. In such cases, we need overlay networks to facilitate pod-to-pod connectivity. And in this lesson, we will look at why that's the case and how Calico implements overlay networks. So let's get started. Okay, so first of all, let's start by inspecting the topology. Now, if you've been following this series in sequence, this lab is going to be a bit different to the previous labs that we've deployed. And that's because we are creating multiple network VLANs to simulate a scenario where the nodes in the cluster are in different network segments. Okay. So if you look at this topology, I have a kind cluster with 4 nodes, 1 control and 3 worker nodes. And 3 of these nodes, the control node as well as worker 1 and 2, are connected to VLAN 10, and that has a subnet of 10.10.10.0/24. And worker 3 is connected to VLAN 20, which has a subnet of 10.10.20.0/24. And their ETH1 interfaces are connected to this network, and the ETH1 interface will also be used for the Kubernetes cluster as well as pod networking. Now, when Container Lab spins up nodes, it by default creates an ETH0 interface and assigns IP to that as well. In the previous labs, we've used the ETH0 interface as the primary interface of the node for both management as well as the Kubernetes control plane as well as pod networking. But in this case, we're going to be using the ETH1 interface. Now, in Container Labs and in the kind topology that we've deployed, we're using something known as a ext-container, which is a wrapper container around the nodes, which are also containers in kind, that is deployed so that we can create these additional interfaces as well as create certain route entries to facilitate communication for these 2 network segments. Okay. So if I go back to the lab guide and if I do a Container Lab inspect topology, the output on the right hand side is going to be a bit verbose. So I'm going to rely on the lab guide here to provide a bit of an explanation. So in this lab guide, I have the 4 node Kubernetes cluster that we looked at, as well as the ext-container. So this, think of it as a wrapper container. If you look at the IPs, they have the same IPs as the nodes deployed by the kind cluster. Okay. And if I go to the topology file, what you're going to see is we have the kind cluster and we have these ext containers, which are going to bind into the relevant kind nodes. And I'm then able to provision additional interfaces, right? So you see me provisioning the ETH1 interface as well as some route entries so that we can facilitate routing between the nodes in these 2 network segments that are created in this topology. Okay. So in addition to the kind nodes, we also have an Arista CEOS image, which I'm using as the router for this lab. Now there's a separate video that goes through how you can import the Arista image. You need to create an account in the Arista portal, download their image and import it to this lab. I don't provide the image in the Git repo, although the deploy script is provided. You need to download the image and include the image in your particular folder so that the deploy script can import it from there to spin up this topology, and that's covered in a separate video. I'll add a link to that video down below. So let me clear this. This is what the topology file looks like. Now I do have some startup config. So if I do a cd startup, we have a startup config for the CEOS image. And what this essentially does is I have the different ETH1 interfaces connected to Ethernet interfaces in this Arista image. Think of this as a switch, a layer 3 switch to which these interfaces are connected. So ETH1 in the control plane node is connected to ETH1, Ethernet 1 in the Arista switch. And in worker 1, it's connected to Ethernet 2. Worker 2 is connected to Ethernet 3, and worker 3 is connected to Ethernet 4. Now, the first three interfaces over here are in VLAN 10. However, Ethernet 4, which is the interface connected to worker 3, is in VLAN 20, right? And if you look at the VLAN interfaces, so VLAN 10 has an IP address of 10.10.10.1, and VLAN 20 has an IP address of 10.10.20.1. So if you look at the topology file, we see these two VLAN interfaces in the router. So given that the router is connected to both segments, it's able to route between these two segments, and we will look at how the overlay network is established to facilitate pod-to-pod communication in this type of setup. Okay. All right. So next, let's go ahead and validate some of these configs. So I am going to clear this, and let's go back and exec into the Arista container. And if I do a show interface status, I'll be able to see the 4 interfaces in the Arista container. These are connected to the respective ETH1 interfaces in the nodes mentioned over here. And as we saw previously, the first 3 interfaces are in VLAN 10, and the fourth interface rather is in VLAN 20, the one that belongs to worker node 3 in this case. And if I do a show IP interface, let me do a show IP interface brief, we see the layer 3 interfaces configured for this particular Arista container. So we have the management interface, which was provided by Container Labs. And we also have VLAN 10 and 20, which are the interfaces that we created for the 2 network segments available in our topology. So let me clear this. And if I do a show IP route, we see that 10.10.10.0.24 and 10.20.0.24 are considered directly connected to this particular router. Thereby, you need not configure any other route statically or dynamically. This router will be able to route between these 2 network segments. So let me next exit out of this, and let's explore the Calico IP pool resource. Now, when we deploy a topology, and we've done this previously as well, there's a folder here called Calico CNI config, and in that folder, there is a custom resources manifest. So when you look at that manifest, when we spin up Calico, we provide an IP pool definition, right? And this IP pool gets configured in the cluster. So if I go to the cluster and if I do a kubectl get IP pools, I am going to receive this output. Now, there are a few important configuration parameters in this custom resource. And the important one for this lab is this one over here called VXLAN mode cross subnet. And we will look at what we mean by this shortly. Now, in addition to a VXLAN mode, we also have the CIDR range as well as the block size. The CIDR range corresponds with the pod CIDR range as well, and we looked at this previously in the IPAM lesson. Now, Calico offers several overlay options, IP-IP being one of those. In this case, we've turned off IP-IP, and we will be exploring VXLAN instead. Okay. So those definitions can be specified in the IP pool, and that will determine what type of overlay network and how those overlay networks are spun up for your cluster. And now let's look at the block affinities for this cluster. So these are the block affinities. Just keep these in mind as we go through the subsequent outputs. A point to note here is that the block affinities in your cluster are going to be different to my cluster, right? So the IP addresses, the block ranges, and in this case, even the MAC addresses that I use are going to be different. The idea is that you follow along, follow the lab guide, and as you execute the subsequent commands, make sure that you replace those commands with the output seen in your lab. So these are the IPAM blocks that are allocated to the nodes in this particular cluster. Okay. So what I'm going to do next is I'm going to exec into worker node 1. So in the subsequent section, we're essentially going to be validating or verifying pod routing between the nodes in the cluster. So let's first do this for 2 nodes in the same subnet. Okay, so in my topology file here, let me expand this a bit. I have worker 1 and worker 2. And remember that worker 1 and worker 2 belong to the same subnet. So the ETH1 interface in worker 1 is 10.10.10.11. And the ETH1 interface in worker 2 is 10.10.10.20. 12. Okay, so let's first verify pod-to-pod routing between these two nodes. So what I'm going to do next is I'm going to exec into worker 1. And in worker 1, if you do a IP route grep/26, which is the mask, we're essentially grepping for the routes that are configured for the IPAM block affinities. And we go through this in detail in one of the previous lessons where we looked at pod routing. So if you look at the block affinity to worker 2, which is 192.168.164.128, right? We can see this particular route. And if you look at the route, we have the block or the prefix in this case, and the next hop is 10.10.10.12. 10.10.10.12 happens to be the next hop of worker 2, right? So essentially in the routing table for the IPAM block assigned to worker 2, and remember the pods in worker 2 will receive an IP from that IPAM block when worker, or rather when worker node 1 or the pods in worker node 1 have to communicate with pods in worker node 2, those packets will be forwarded to the ETH1 interface, right? Now, when the packet is forwarded to the ETH1 interface, if we zoom in a bit here to the structure of that packet is going to have the original source IP of the pod that initiated the traffic, okay, as well as the original destination IP of the pod that to which the traffic is destined, as well as the source MAC address as it egresses the node of the ETH1 interface and the destination MAC address of the ETH1 interface of worker 2, which is the destination node in this case, right? So this is what the packet would look like when the nodes are in the same network segment. So essentially, there is no external component that has to evaluate this packet to make a forwarding decision, given that these are in the same segment. We can do, or rather replace the MAC addresses and send the packet, and the packet will be received by worker 2. Okay. All right. So if I exec into worker 2, so let me exit from this output here. And if we exec into worker 2, and if we grep the /26 routes, and if I look at the affinity to worker 1, which was 192.168.81.64, if we look at that particular route, we can see that the next hop is 10.10.10.11, which is the IP address of the ETH1 interface in worker 1, right? So bidirectional routing is configured in this case, and essentially the packet or the format of the packet would be the same. So that's how routing happens, pod-to-pod routing happens when your nodes are in the same subnet. So next, let's take a scenario where the nodes are in different subnets. So for this example, we're going to take or consider worker 1 and worker 3, okay? All right, so back to the lab guide. So first of all, I am going to exec into worker 1. So let me come out of this. Let's clear the screen, exec into worker 1. So sorry, so I just realized I had a typo there. So worker 1 is essentially worker, right? That's how the kind nodes are deployed. So let me clear my screen. So I'm currently in worker 1. I will correct this in the final version of this lab guide. And in worker 1, if I do a IP ADDR and grep for vxlan.calico, what you're going to see is that there is a vxlan interface provisioned, and you're going to see this in all of the nodes in this cluster. And if you look at the IP of that vxlan interface, which is 192.168.81.64, what you're going to notice is that that IP is essentially the first IP of the block that was assigned to that particular worker node, right? So when you configure IP pools in Calico, what you might have noticed is there is this allowed use section in the IP pool. And in this particular definition, we are allowing the use of the IPs in this IP pool for workloads, which are pods, as well as tunnel interfaces. Now you can have separate IP pools, one specific to workloads and one specific to tunnels. But in this case, we are using it for both. And when this happens, Calico typically assigns the first IP of a block assigned to a node for the tunnel interface. So if you look at this block, the first IP is 192.168.81.64/32, which we see as the IP assigned to the VXLAN interface in worker 1. Okay. All right, let's go back to the guide. Now, if I do a IP route grep to 192.168.209.64, now 192.168.209.64 is the block affinity assigned to worker 3. Okay, so if I grep that, what you're going to notice is this route is a bit different compared to the previous routes that we saw. And this one, if you look at the prefix, this was the block assigned to worker 3. It's routed via 192.168.209.64, and it's routed via this particular link, which is vxlan.calico, right? So it's routed through the vxlan link. So let me go back to my diagram to highlight some concepts here. When you have an overlay network configured, in this case VXLAN, as we discussed previously, this VXLAN interface is going to be provisioned in each of the nodes, each of the cluster nodes, and that interface is going to have an IP address, which is typically the first IP of the block assigned to that particular cluster node. So in the case of worker 1, the IP is 192.168.81.64. In the case of worker 2, the IP is 192.168.209.64. So if you look at the route here, it says for the 192.168.209.64 prefix, the next hop is 192.168.209.64, which is the IP of the VXLAN interface, right? So the routing table now kind of offloads the process of forwarding this packet to VXLAN. So it's not the typical routing logic that follows afterwards, but rather a VXLAN forwarding decision that has to be made. And we will look at how that packet is going to be formulated next. Okay. All right. So that is the routing table. Let's go back to the lab guide. All right, so next in the lab guide, what I'm going to do is I am going to exit from here and I am going to exec into worker 3. So remember, worker 3 is the node that is on a different subnet. And in worker 3, if I do a IP ADDR grep for the VXLAN interface, this is 192.168.209.64 is the IP of that interface. And if I do a IP route grep, what you're going to see is all the routes here have VXLAN as the forwarding mechanism. And that's because unlike the nodes that are in the same subnet, worker 3 has to have VXLAN tunnels to forward traffic to all other worker nodes. So in the routes here, we're going to see VXLAN to every other node in the VLAN 10 segment. Whereas if you look at these nodes that are in VLAN 10, it only needs one VXLAN tunnel interface towards worker 3, right? So when you look at the routing table output for worker 3, it is going to be different compared to the routing table outputs we saw for worker 1 or worker 2, okay? All right, so next what we're going to do is we're going to look at the VXLAN forwarding logic. So we are currently in worker 3. And when you look at the routing table, what we realized was that the next hop is the corresponding VXLAN interface of the remote node, right? Now, you can't just send a packet to that VXLAN interface because your underlying network is not aware of this VXLAN interface, right? So this upstream router is not aware of your pod IPs, nor is it aware of the VXLAN interface IPs. All it is aware of are the IP addresses of ETH1, which is in VLAN 10, and ETH1 of worker node 3, which is in VLAN 20, right? So these IPs are like first-class citizens as far as this network is concerned, but your pod IPs are not. So if you send a packet, as we did previously, where the source and the destination IP were the original IPs of the pod that initiated the traffic and the pod to which the traffic is destined, this router is going to drop that traffic because as far as this router is concerned, this one over here, those IPs are not known IPs. So the traffic is going to get black holed. Okay. So next, we're going to look at, how this packet gets formulated in a way that this router can forward it to worker node 3 if the traffic was originated by a pod in worker node 1. Okay. All right. So I am currently in worker node 3. And what I'm going to do is if I do a IP link show type VXLAN, this is the VXLAN interface. And what you're going to see is this VXLAN interface has a particular MAC address, so do the other VXLAN interfaces configured in the other nodes. Now, if I do a IP neighbor show and grep for VXLAN, what you're going to see is for each VXLAN interface that's configured across your cluster, Calico will populate this table, and this table has the IP of those VXLAN interfaces along with the corresponding MAC addresses, right? So for each VXLAN interface, so I'm right now in worker node 3. So I'm in worker node 3. But remember, every node in the cluster has a VXLAN interface, and those interfaces have a MAC address. And Calico in each node's neighbor table will configure or populate the IP address of every other node's VXLAN interface along with the MAC address of that interface. So if you go to any other worker node or the control plane node and execute this command, you're going to see a similar output for all the other nodes in the cluster. Now, if I select a particular interface, so if I go back to my diagram, the IP of the interface that belonged to worker 1 was 192.168.81.64, right? So 192.168.81.64. So this is the interface IP, and this is the MAC address of that interface. If I do a bridge forward DB show for that particular MAC address, it's going to show me what the destination IP is, right? .11, if I zoom this in a bit, is the IP address of the ETH1 interface of worker 1. Now, just a slight correction to make here. When I was recording, I noticed that the IP addresses in this image was incorrect. So just to clarify, the IP address of the ETH1 interface in worker 1 is 10.10.10.11. And the IP address of the ETH1 interface in worker 3, which is the interface or the worker node in a separate subnet or segment, is 10.10.20.20. Okay, so you might, if you pay attention to the diagrams, notice that there was a typo there, which I have corrected in the final version. Just bear that in mind, but that doesn't change anything that we discussed or anything that I presented in this video. Okay. So when we looked at the forwarding table here, we see the MAC address, right? The MAC address for the VXLAN interface. And for that MAC address, we see that the destination is worker 1, which is 10.10.10, the ETH1 interface of worker 1. Now, what we can do is we can do a similar lookup from worker 1. So let's do that. So let me exit from here and let me exec into worker 1, and right, so right now I'm in worker 1. If I do a show IP link, and this is the VXLAN interface, and this is the MAC address of the VXLAN interface deployed in worker 1. And if I do a show IP neighbor, right, we see the corresponding or the remote VXLAN interfaces as well, along with the IPs of those interfaces and the MAC address. And if I look at the IP of the interface that was configured in worker 3, it is 192.168.209.64. So if I do a bridge FTP show, so 209.64, I copy this MAC address and paste it here. Sorry, just give me 1 sec. I'm just gonna grep it. All right, we can see that the next hop, the destination is 10.10.20.20, which is the IP address of the ETH1 interface of worker 3, right? So now let's look at how this packet gets formulated. So we looked at how the forwarding decision is made. And essentially, this is what the VXLAN packet is going to look like. So we have the original layer 3 headers with the source IP and the destination IP of the pods, and I've tried to color coordinate this as well, and hopefully that's easier to understand, right? So we have the source IP, destination IP. This is the original packet, right? And next we have the Ethernet headers. Now remember, this packet is coming to this VXLAN interfaces. So you're going to see like Ethernet headers corresponding to the MAC addresses of those VXLAN interfaces. And then you're going to see some VXLAN headers as well, right? However, there's also going to be this outer packet, right? So this packet, okay, all of this information is going to get encapsulated with this information over here. So as this packet comes out, it's going to have a source IP corresponding to the IP of ETH1 and a destination IP corresponding to the IP of ETH1 worker 3. So source IP ETH1 worker 1, destination IP ETH1 worker 3, and the Ethernet headers, the layer 2 headers, right? So when it comes to the layer 2 headers, it's going to change throughout the different hops this packet has to navigate through. But essentially, like what's going to happen is if you look at worker 1, right? So worker 1 knows that this is the next hop, right? If I do a IP route get to 10.10.20.20, what this worker 1 is going to do is to reach 10.2020, right? Remember, this is a separate network subnet. It's going to send that packet to 10.10.10.1, which is this interface in the upstream router, 10.10.10.1, right? So as this packet comes out, it's going to have, as the source MAC, it's going to have MAC A, and the destination MAC will correspond to the MAC of the interface of the particular router. So the packet lands here, right? And then the router makes a routing decision to forward the packet to the ETH1 interface, at which time the destination MAC will change to the MAC address of the ETH1 interface of worker 3. But that's not important. The MAC addresses are not as important. What I want to highlight is if you look at the structure of this packet, this is the original pod that sent the traffic. This is the pod to which it's destined. These are the Ethernet headers of the VXLAN interfaces. And the source IP is going to be the IP of ETH1 worker 1. The destination IP is going to be the IP of ETH1 worker 3. And when worker 3 receives this packet, it's going to remove these IP headers and look at the VXLAN information. And it's going to realize that this packet is destined to the VXLAN interface. It's going to forward that to VXLAN, at which point VXLAN analyzes the packet and it removes these header information, after which the only thing that's revealed is the destination IP and the source IP of the pod that sends the traffic. And given that we have a route to the destination IP or the destination pod, that traffic is then handed over to the route table lookup in this particular node, after which the traffic goes to the destination pod. Okay, so that is how the VXLAN packet is created. And the whole objective of creating this packet is to ensure that this router doesn't see the source and destination IP, because these IPs in yellow are not available to your network. So if the router sees this, it's going to drop that packet. So what we rather do is encapsulate that packet inside a VXLAN packet and send the packet as if it's coming from this particular node, destined to this particular node, which the router is aware of, right? All right, so, there you have it. That's why we need overlay networks in Kubernetes. Now, our overlay was configured as VXLAN cross subnet. So essentially what we saw was an overlay network only when your node is in a separate segment. However, with Calico, you can have VXLAN overlays even if your nodes are in the same segment, right? So if you say overlay or encapsulation, VXLAN mode always, and I'll add a link to the docs as well that goes through the different configurations. You could have overlay across all the nodes in the cluster, regardless of which segment they are in. However, I chose VXLAN cross subnet to also demonstrate the fact that it is a feature that's available and how overlays would work when nodes are in different subnets, right? So that's it for this lesson. I hope you enjoyed it, and I'll see you in the next one. Thanks for watching, and bye for now.